Hello everyone. Today in this video I'll be discussing about a problem from Pathfinder Work Power Energy. Check your understanding. Question number 2. Well, initially when I looked at this problem I thought it's a bit complicated because it involves a lot of approximations and a little bit concept why the angle theta which is asked in the question is a constant rather or it's a variable with time. I always thought about it. So, today I'll be clarifying all the doubts you may have regarding this problem, or probably you might have solved this problem previously. Those who haven't solved it, you can give it a try, pause the video, and I'll be starting in a few seconds. So, let's get started. The problem says that you have a particle like ball which is connected to one end of an inextensible cord. The other end is connected to a thin frictionless vertical rod. The entire length of the cord is wound around the rod into a large number of closely spaced turns. The ball is held touching the rod. When the ball is released, the cord gradually unwinds and the ball starts to circle around the rod. You have to find the angle which cord makes while it's unwinding with the rod. Okay, so it's actually asking the angle after a long time. After a certain long time, you have to tell me the angle between the cord and the rod, so that this actually asking the steady state angle, right? So what happens basically is that you have a rod. I'm marking the rod with a blue color, and you have very small turns, very small, very thin and closely spaced turns. You can assume these turns which have a pitch of h, and another thing is that the radius of this rod is r. So one assumption we have to do before solving this problem is that the h is much less than r. So one assumption is very important to solve this problem. Now what happens basically here that you have the ball here. Suppose it's the radius of the circling is r. Okay, I'm assuming the radius to be some r or capital R. Let us assume, because I'm assuming smaller to be the radius of the rod. So let us assume that now the ball is circling around the rod with the radius of circle of capital R. Now basically what happens is after one turn completes, then it will be something like this. The situation will be like it will go by some distance h upwards, and what is unwinded length? Unwinded length, that is L, is equals to 2 pi r under root 2 pi r whole square plus h square. Basically, more specifically, we can write it like this, right? So it will go upward by h and downward by 2 pi r whole square plus h square under root cos theta. This cos theta is important while doing this problem. Basically downward by L, so it will go downward, means vertically displacement will be L cos theta, delta H will be L cos theta minus H. So work done by gravity would be mg into L cos theta minus H, right? Now another thing is that, let me ask you a simple question. Is angular momentum conserved here about the central axis of the thin rod? Quick question to the viewers. Think for some time and I'm presenting the answer. Well, the answer is no. The angular momentum is not conserved. Why? You might have come across through this question that you have a cylindrical something, you can say a cylindrical heavy mass or a fixed cylinder, and here's a string, and here's a you can say a disk, a frictionless small disk which has a finite mass m, and this cylinder is fixed. Now, you might have come across this question that when you are given a velocity v, it is from Irodov. Now, when this is given a velocity v and this has length L and radius is r, you are asked to find the time to wind around the cylinder. Well, I'm not going to find the time in this question, but I'm giving you some hints. The hints is that when you consider it has winded by some angle, it has winded by some length and it has gone through some angle, then Herodotus says that here the velocity is v. The velocity is v, not v dash. That is, the velocity is unchanged because tension is acting perpendicular and there is no displacement in the direction of tension, right? So basically, there's no work done on the system, on the puck, you can say, or the disk. So the velocity v will be constant, which will be v naught. Now, I'm asking you one thing. Here the length is L, and here length will be L minus r theta. So initially, with respect to this point, Li is equals to mvl, Lf is equals to mv L minus r theta. These two are not same. So that is why here also, in this case also, the velocity will not be same because the work is done by the gravity, but angular momentum will not also be same. You can say that work is done by the gravity and it's finite, so the velocity will not remain same, unlike the Herodov problem. You might be wondering about another problem, that is, here we have a table and we have a small hole here. This is a string and you have a disk, another again a disk, and it is moving with velocity v. Then when we try to pull this string downwards, then we say angular momentum is conserved. But why we say? Because in this case, string does some work when it's decreasing its radius, that is the radial distance from the hole, by some L dash. Okay. Initially it was L, then it went to L dash. So basically some work is done by the string and it's finite. Hence we say, in this case the velocity will not be same because work is done by the string. But in this case the velocity is always perpendicular to the tension force due to the string. Hence there is no work done by the string in this case. Now back to the question, I have explained you few concepts regarding other problems which are helpful to understand and analyze this problem. Hope you get it. So this is the work done by gravity. Now you see that it's circling, so there will be force balance also. By force balance, you can say that mv square by r is equals to mg tan theta. You can derive it easily because it's revolving around a circle of radius r, and by using basic geometry also you can find it, because here it's mg and here is mv square by r, and this makes an angle theta because the tension force will basically cancel all of them, and you can basically, this is also known as the famous Lamis theorem. You can also apply the Lamis theorem to find it. So basically we'll get kinetic energy is equals to mgr tan theta. Now if you descend, if the ball descends by L along the direction of the string, so the displacement along the x direction will be L sine theta. So delta k would be mg L sine theta tan theta, and delta k is equals to delta u. You will get this equal to mg L sine theta tan theta, right? Now one thing I'd like to say about this problem, a small thing, that here we need to assume that r is much greater than h. So I'll write L to be nearly 2 pi r. First thing. Second thing, that L cos theta minus h is nearly L cos theta. These are two assumptions which must be, I think, mentioned in the problem. Well, they have said that these are very closely packed terms, so we can neglect the value of pitch, that is h. But still, I think that these kind of parameters must be mentioned in the problem. Uh, Getting back, we'll get 2 pi here. Yeah, we'll get 2 pi r mg. We'll get 2 pi r mg cos theta is equals to mgl sin theta tan theta. Hope you get it. Yeah, a small problem here that it will be there will be a factor of half here. K will be mgr by 2 tan theta. So delta k will have a factor of 2, and we can just keep it L as it is, and here will be a factor of 2. So you will get, cancelling all the common terms, will get tan theta is equals to root 2. So theta will come out to be tan inverse root 2, and that's the answer. Now in the thumbnail I have also given that why the theta angle is a constant value, why it's a steady state value. Now you might have come across a chapter which is known as the principle of mathematical induction in your class 11, 12 or the high school. So what this principle of mathematical induction says, that if Pn is true and Pn plus 1 is true, then P is true. Basically, if Pn is true and Pn plus 1 is true, then P is true. This is what happens in case of mathematical induction. Now let us assume that after a long time, the situation is something like this. This is the rod, and here's my turns, and this is my nth turn. This is my nth turn, which has unwinded. In this case, the angle is theta. Now, in the next turn, that is Pn plus 1, let us assume that the angle changed by some theta plus delta theta, right? So we can say that if first we'll be getting two cases. First case says that delta theta is positive. Now what happens basically, then theta will try to increase and increase. Since it's a long time, then it may happen in the later time that delta theta tends towards 0. Then we'll get some steady state, and we want that only. So, or another thing can happen, that delta theta is constantly positive, then theta plus delta theta, then theta plus delta theta plus delta theta dash in the n plus 2 turn, and so on. If all of these are finite, then what happens, that the bead will go like this, means it will turn by 90 degrees and it will go beyond that angle, which is practically impossible. So you can say that this assumption is wrong. And the second assumption is delta theta is less than 0. Basically what will happen, that the bead comes towards the rod, right? In this case also you can assume that this summation of delta theta converges. Then that's the case which we want. So basically no requirement of dealing with that. But if delta theta does not converge, then what will happen, after a certain moment of time, it will be like this. Now the thing is that the velocity is increasing because work is done by gravity. The string is unwinding and it's moving around this rod, you can say. So now this creates a kind of a paradox. You'll have a velocity in the tangential direction vt, and the radius is very small. So vt by r square is a very large term, okay? And mg is a finite term. So vt by r square will be much greater than mg, because vt is finite and r is very small as mentioned in the question. So this will be a very large term, and we know j is just 10 or 9.8 meter per second square. So this assumption is also a wrong one. I guess you all guessed and got the answer, that why theta converges or becomes a constant value. Hope you enjoyed today's video. I'll be bringing up more problems and some other interesting concepts. Stay tuned and have a nice day.